Okay, here we're going to do a quick review of Chapter 15, talking about energy and chemical changes. We're going to talk about energy and heat in this one. So remember that energy is the ability to do work or to produce heat. There are two forms of energy that exist, potential and kinetic. Potential energy is due to composition or position. Kinetic energy is energy of motion. So right here, the water in the reservoir has potential energy, and the water that is running through the water intake and spinning the turbine and into the river has kinetic energy because it is moving. And remember, the law of conservation of energy states that in any chemical reaction or physical process, energy can be converted from one form to another, but it is neither created nor destroyed. This is the first law of thermodynamics. So, energy can neither be created nor destroyed. It is only conserved or transferred or converted. Any of those words would work. When we talk about chemical potential energy, this is a type of potential energy. And remember, it is not moving energy, it is stored energy. And this is energy stored in a substance because of composition. So a candle has chemical potential energy. Food has chemical potential energy. Think back to the calorimetry lab. Peanuts have more chemical potential energy than marshmallows. That's why the peanut burned for longer. It's important in our chemical reactions because typically it comes out as heat. And heat is energy that is in the process of flowing from a warmer object to a cooler object. Q symbolizes heat. So if you put your hand on your desk, the heat is flowing from your hand to the desk because your hand is warmer than the desk is. It's going to keep flowing. It's not going to stop flowing when they reach equilibrium. Then it'll flow back and forth at equal rates. But you'll stop feeling that flow of energy when the desk has the same average kinetic energy as your hand. When we measure heat, typically we're going to use little c calories, and that's the amount of energy required to raise the temperature of 1 gram of water 1 degree Celsius. But this is where things get confusing. There are 1,000 heat calories in a nutritional calorie that we measure food in. Nutritional calories are also measured in kilocalories in other countries other than the United States. And that makes sense because the prefix kilo means that it is 1,000 times bigger than the base. So you've got 1,000 heat calories in a nutritional calorie. You've got 1,000 heat calories in a kilocalorie, which means that a nutritional calorie is equal to a kilocalorie. But we don't use calories that often except for when talking about food. We use joules because that is the SI unit of heat and energy. Remember that 1 heat calorie is equal to 4.184 joules. And here's just a table that has all of those. You will need to make sure that you know this one and that one. And that there are 1,000 heat calories in a kilocalorie. So right here, we did this one in class, but if we have 230 nutritional calories, and the question is how many heat calories do we have, we would just set up a conversion, 230 nutritional calories to heat calories, and heat calories is a little c, nutritional calories is a big C. There is 1 nutritional calorie for every 1,000 heat calories, so my answer would be 230,000 little c heat calories. If I wanted to know how many nutritional calories there were in a kilocalorie, well, I would think back, and they are equal to each other. So the answer would be 230 kilocalories. But then if it said how many joules, well, I can't go directly from nutritional calories to joules, but I could go big C, nutritional calories, to little c, heat calories, to joules. So I would set that up as a 2-step problem. 230 big C calories to little c calories, and then little c heat calories to joules. With the one with big C calories, 1,000 with the little heat calories, and then the one with heat calories for every 4.184 joules. It's like putting together a jigsaw puzzle. So I can do 230 times 1,000 times 4.184, And my answer would be 962,320 joules. So that's how I convert between calories, kilocalories, and joules. So, switching gears a little bit, specific heat is the amount of heat required to raise 1 gram of a substance 1 degree Celsius. Some objects require more heat than others to raise their temperature. Water is going to require a lot of heat because it has a high specific heat. Gold and all other metals are pretty low. Most metals are below 1 for their specific heats. They do not require a whole lot of heat to start heating them up, just because they can't hold that much heat. So remember that the wood, I don't have the black box, but that wood has a higher specific heat than plastic. So that means wood can hold more heat. It would take a longer time to heat up. The sidewalk has a lower specific heat than pool water. So since pool water has a higher specific heat, it's going to take a longer time to heat up. So if something heats up quickly, it has a low specific heat. Specific heat is just how much heat is required to raise 1 gram of that substance 1 degree Celsius. Excuse me. So when we calculate heat absorbed and released, we use the equation Q equals C times M times delta T, or Q equals M times C times delta T. Either works. Q stands for heat absorbed or released. We're typically going to use joules. C is the specific heat, and you always can look that up on chart 15.2 that, remember, is on your thermochemistry reference sheet. And M stands for mass in grams, and delta T is the change in temperature. That means you're going to subtract, so you get the difference. So right here it says a temperature of a sample of iron with a mass of 10 grams changed from 50.4 degrees Celsius to 25 degrees Celsius with a release of 114 joules. What is the specific heat of iron? So anytime it asks me for specific heat, I know I'm using the equation Q equals M times C times delta T. Q is measured in joules, that's 114. M is 10 grams. C is what I'm looking for, and the change in temperature is going to be 50.4 degrees Celsius minus 25 degrees Celsius. And that's going to be 25.4 degrees Celsius right there. So I'm going to solve, and I'm going to do 114 divided by 10 divided by 25.4. And my answer would be 0.45 joules divided by grams times degrees Celsius. If you forget the units, don't worry, you can look at the top of table 15.2. Here's a second one. It says how much heat is absorbed by a sample of concrete weighing 5.2 kilograms if the temperature increases by 6.0 degrees Celsius. So it's asking me about heat, and it gives me a temperature and a mass. So Q equals MC delta T. I'm looking for Q. It gives me a mass of 5.2 kilograms. I need to convert kilograms to grams. And remember, kilo means 1,000 of the base unit. So that's going to be 5,200 grams. That's my mass. Specific heat for concrete, I'm going to look up on my thermochemistry reference sheet. So I'm going to look up on the thermochemistry reference sheet. It is, concrete is 0.84. So I use that as my specific heat. Joules divided by grams times degrees Celsius. And my temperature change is 6 degrees Celsius. So I'm going to multiply that, 5,200 times 0.84 times 6, and my answer is 26,208 joules. That's how you do the Q equation. Now, when we did the lab, when we lit the Cheetos on fire, we use a calorimeter. And the calorimeter is an insulated device used for measuring the amount of heat absorbed or released in a chemical reaction or physical process. So right here, this is the bomb in the middle. That's your reaction chamber. The water around it is the insulation. So you burn whatever is in the reaction chamber, and the heat released by that is absorbed by the water. So, right here, I'm going to let you pause and do this. This would be asking what the specific heat of this metal is, and you're going to use the Q equation. And your answer would end up being 0.3 joules divided by grams times degrees Celsius. If you have a question on that one, go back and look at your notes. So here, this one gives me 1, 2, 3, 4, 5 different numbers. Well, when I'm using the Q equation, what that means is that the heat lost by the metal is equal to the heat gained by the water. So I could rewrite that as the mass of the metal times the specific heat of the metal times the temperature change of the metal is equal to the mass of the water times the specific heat of the water times the temperature change of the water. When I look up here, it tells me I have a 15-gram piece of metal. It's at 100 degrees Celsius. And the final temperature is 23.3 degrees Celsius. So I'm going to do 100 minus 23.3. I'm looking for the specific heat of the metal. It tells me the mass of the water is 100 grams. I look up on my thermochemistry reference sheet that the specific heat of water is 4.184 joules divided by grams times degrees Celsius. And the water starts at 20.0 grams. Excuse me, that should not say grams, that should say degrees Celsius. And I'm going to subtract 23.3. I want to take the absolute value of that. I want it to be a positive number. Right here, this is going to be 76.7. Over here, this is going to be 3.3. So what I'm going to do is I'm going to do 100 times 4.184 times 3.3. And then I'm going to divide that by 15. And then I'm going to divide that by 76.7. And my specific heat for this metal is 1.2 joules divided by grams times degrees Celsius. Because remember, the law of conservation of energy is the energy lost by the metal was gained by the water. Going back to the calorimeter, what is lost in the reaction chamber is gained by the water. So when we're talking about thermochemistry, we're talking about heat changes that accompany chemical reactions. The system is what we study. That would be like the metal in the previous example. And the surroundings are everything else. That would be like the water in the previous example. Together, those make the universe. So when we talk about the law of conservation of energy, the heat lost by the system equals the heat gained by the surroundings. And that is where we're going to stop right now. Thanks for your attention.